This is the video solution for exam 3. Now this first problem is a translation problem. It's a vehicle under, and this one is under braking condition, but we started chapter 17 talking about braking and accelerating and the differences there. But what we understand was that the normal forces tend to change a bit because they're under acceleration or under a braking condition. If we're looking for the maximum braking condition or shortest stopping distance or something like that, then we're also talking about the slip condition, where in the slip condition, the point, the normal for, or sorry, the force of friction then will be mu normal wherever the friction forces are applied. So anyway, the first thing we want to do is draw a free body diagram. Got an inclined plane, mg sine theta, mg cosine theta, normal forces. The force of friction has to be applied or should be applied at the point where they really are applied, which is the front brakes. The MA vector is also very important. This is part of the free body diagram. If you did not draw an MA vector, it is not a complete free body diagram. Direction of positive is also important, and I often will draw the positive direction in the direction that acceleration is going. So anyway, so we will start this with some of the forces in the x is mass times acceleration in the x. Again, the force of friction will be mu normal at that point. We can solve that for A. And then we'll do a moment equation. Moment equation, again, we can sum the moments about either point, A or B, but as often the case, if I'm looking for the normal force at A, then you can save an equation if you sum the moments about B. Now, a lot of you sum the moments about G, which is also very appropriate. You can do that, but you do have to have another equation to do that. If you sum the moments about B, then you can solve for the normal force at A uh, with just the force equation and the moment equation. You don't have to do another equation in the y. But at any rate, let's sum the moments about B. Let's define a positive direction. I'm going to go this way is positive, so that means, let's put this back down a little bit. This mg cosine theta and mg sine thetas are going to be both negative. Then A times this lever arm is going to be in the positive direction, and then the MA vector will be positive. When we do that, we can do two equations, two unknowns, and find the acceleration is 2.068. To find the stopping distance, this is a constant acceleration equation, and you can find that. Okay, this next problem is a tip and slip problem. Again, we did several of these, but in this case, what we're looking for is the maximum pulling force, P. Let's draw a free body diagram of just the box. In this case, the force of friction, MA vector, MG. This is a tip or slip problem. So at slip, we know that the force of friction is mu normal. And in this case, mu mg. So we'll solve that for the slip condition, just like that. At tip, it tends to rotate about this point. It will tip over backwards. And so what we say is that tip, it rotates at A, and whatever over here is goes to zero. B goes to zero. So it's often easiest to sum the moments about the point of rotation. I'm going to go counterclockwise as positive. So mg is negative and ma vector is negative. You can find the tip acceleration. Now, so what happens first? Well, clearly the tip acceleration is lower, so that's got to be what happens first. So a pulling force is what we're looking for. So we're going to say this is the acceleration of our system. I'm going to pull with some force to accelerate it at that system. So that's how it takes. You accelerate all 150 pounds. Now, if you want to know the force of friction, however, you only look at the box. Isolate the box. The force of friction is what moves the box forward. And so the force of friction then is going to be the mass of the box only times that acceleration. So again, it's not a slip condition. It is not mu normal. It is this acceleration right here. All right, this next one, let's get this over just a little bit. This next one is a two center of gravity problem. In this one, you have to draw, it's appropriate to draw two MA vectors and two MGs, right, like this. So again, this is a maximum acceleration system. We're looking for the normal force at A. The force of friction should be applied at the rear tires. You can sum the forces in the x as mass times acceleration in the x, and as the system, all 3,000 kilograms are moving forward. To find the normal force at A, some of the moments about B. We've got a couple of mg's here. About B, we got this mg, that mg, both of those are positive. A is negative, the two ma vectors are negative. Two equations, two unknowns, and go ahead and solve that. Then find the normal forces. You can get the normal force for the A out of this set of equations, and then sum the forces in the Y to get the output. This one is the fixed axis rotation problem. And we got an mg here and an mg there. And what we're saying is we're going to release it from rest. It's got a torque here, and it should begin to accelerate. Let me draw a little acceleration vector, something like that. And so here's our equation. Sum of the moments about A is IA alpha. So let's find IA first. And I about A is using the parallel axis there. And what we're finding is the moment of inertia of the system about that point. So the bar is 1/3 ml squared, and the disk is 1/2 mr squared plus md squared, where this is the distance you're moving. Now, a lot of you messed up this 1/3 ml squared, and let me just explain that briefly. If a bar is rotating about its end, it is 1/3 ml squared. If you want to, you're certainly welcome to use 1/12 ml squared plus md squared. And if you were to do that, then you'd get the same value or same numbers when you get done with it. But again, several use 1/3 ml squared plus md squared, and plus md squared, which is redundant, and that would give you the wrong answer. Or if you'd use 1/12 ml squared and didn't use the md squared, didn't use the parallel axis theorem, that was incorrect as well. So once we find IA, then the moments we just have mg times this lever arm and this mg times this lever arm plus that 30, and we get alpha. All right, so this next one was the angular acceleration equation problem. Understanding acceleration of A probably goes this way. I gave you the acceleration of B was negative, and so A, it would be minus J. Acceleration of B is negative in the I direction. So with our acceleration equation, if you write it with the right order, then you'll get this position vector R of A with respect to B. So where is A if I'm standing on B? Well, it is 4.47 in that direction and 4 in that direction. So minus in the I, positive in the J. Once you do that, then just do the cross product and multiply it out. It's pretty important that you show me the result of the cross product. A lot of people got the wrong answer, and I didn't see this, and so I took off points if I saw some writing, but didn't see this result. So that's kind of important. And then the answers. All right, this next one is a sine cosine problem from our absolute analysis. And so what we're looking for is a right triangle. And so here's our right triangle right here. And that's what I've drawn here is 0.08, and this is the angle theta. This is positive theta. But our total y distance goes all the way up to here. So what we have is that y is actually equal to 0.08 sine theta plus 20, where 20 millimeters is the offset. Taking the two time derivatives, this 20 thousandths goes away. So it turns out to be not a factor when it comes to the actual speed. So solving that, you get 37 or 0.375 and negative 0.608. This one was a by any method you choose. However, there was really only one method that actually worked. A lot of people tried using other methods. They even got the right answer, but if you did not choose the parallel velocity vectors, you were imagining something that wasn't there. In other words, I did not give this angle here. So the actual position of C is unknown. You can see that there's the position of B, but if this angle was 45 degrees, this would have put C in a different position. If this angle was 20 degrees, this would have been in a different position. So the only thing you could really do is understand that VB goes down and this pushes the C down this way and VC goes down in a parallel way here. So parallel velocity vectors was really the only approach. Um, if you got the right answer but didn't use this approach, then I may have taken off some points. And then the last one is just a gear problem. Almost everybody got this right, but understanding that the omega of this one is related to this one by the ratio of the radii. So omega b is actually 33. Then the omega of the inside is equal to the omega of the outside. So the velocity of d going up is the same as the velocity of c going up, which is equal to this little r times this omega, which is 33.